second part of chapter 11, just another ways to use the chi-square distribution. So we saw the goodness of fit and how we could compare. It was just like one categorical variable across like one sample or one population. Now sometimes we get these two-way tables which have two categorical variables, and we need to do some testing on those. So when we have that, we have to use still the chi-square distribution, and we do things kind of a little bit differently. So we are going to be looking at the distribution of the categorical variable across the populations or treatments, and we're going to also look at if there's an association. So when I'm looking at this here, I have a two-way table here, and it's just summarized by the treatments that they were giving with the music, and then the bottles of wine that they purchased. So first thing they kind of say here, let's go back to the past and calculate the conditional distribution and proportion of the type of wine sold for each treatment. So we're going to look at the wine sold for each treatment. So I'm going to do like 30 over 84 and 11 over 84 and so on. And then it says to make a graph, and then the distribution's different. So there's the table again. So when no music was playing, here's the distribution of the wine. So again, we're looking at the distribution by the treatment, not the distribution by the type of wine. So I've got 30 over 84, 11 over 84, 43 over 84, and so on. We can do the same thing for the French music. It'll all be over 75, and the same thing for Italian, which is all over 84 again. And we can look at graphs here. We can kind of get an idea that, okay, well, you know, we can look at a lot of different things here. When no music are playing, people are more likely to buy other and French. When French music is playing, there's still French and other. And finally, when you're playing Italian music, some of that Italian wine shows up a little bit more. And so you can make some conclusions here about that. So what we're going to do here is we're going to take those tables and actually conduct analyses on there. So we're going to look at an overall test to see if there's good evidence among the differences amongst the parameters. So like in the last one, among the different treatments. And then we could do a follow-up analysis to figure out which one is influencing things the most. So we're still going to go back to our chi-squared. The generic form of the null is that there's no difference in the distribution of a categorical variable for several populations or treatments. And the alternative will say that there is a difference for the distribution. So the null is always the hypothesis of no difference. So again, here we have so the null would be here that there's no difference of the wine purchased across the different treatments. We can figure out the expected counts. So 99 of the bottles, well, let's just go to the next page. Alright, so they figure out the proportion of how you do this. So you're looking at let's do it this way. It's always the row total divided by the column total, or times the column total divided by the total amount, and that'll give you the expected counts for that cell right there. So it's like you're saying that out of I would expect 99 over 243 of the bottles purchased to be French. So that's how many I expect to be purchased, and then out of all, there's 84 bottles purchased when no music was being played. So if I take that percentage times 84, this is how many I expect to be French wine with no treatment. So the expected count is always the row total times the column total divided by the table total. We still check our conditions the same way. The test statistic is still the same way. Don't include the total column or the total row. Here's the expected counts here for this one. Here's they do it for each 9 of those cells. to find your p-value, it's always, the chi-square test is always a right-tailed test. The degrees of freedom here are a little bit different. Now it's the number of rows minus 1 times the number of columns minus 1. So degrees of freedom here, so we have 3 rows and 3 columns. So 3 minus 1 times 3 minus 1, so we get 4. I taught you how to use the chi-squared CDF command. So you can use the chi-squared CDF, so 18.28, comma, positive infinity, comma, 4 for the degrees of freedom to get your p-value. So again, and just like before, if the p-value is small or less than your significance level, you reject, and you're able to conclude the alternative. So let's look through this example right here with the cell phones and the landlines. So they just wanted to know if their political preference was different based on if they have a cell phone only or if they had a landline. Looking at the graph here, it doesn't look like they're going to be that different, but the null again, so we just would write this out. So now it's in context, so it's not generic like it was before. So there is no difference in the distribution of party affiliation in the cell only and landline populations. The alternative says that there is a difference. And they're going to pick a significance level since one was not assigned. Alright, so the data came from a separate random sample of 96 cell only and 104 landline users. So in this case, when you're doing the test of homogeneity, you're taking more than one sample from more than one population. So in this case, we're taking 2 samples, so we need to check that both of those are random. Alright, the expected counts, they're coming from this matrix. Remember, you still need to write out the expected counts on the AP exam, so when you are in that step there, make sure you write those out. And I'll go through and show you where those come from once I plug everything in and do the test statistic. Alright, the independent check. So they're sampling without replacement, so we're going to check that there's 960 cell phone users and 1,040 landline users. Alright, to do this test, again, like I said to you before in class, always write out what the first one is, so the first observed minus the expected squared over the expected, all the way up to the last one. Alright, and then here's your p-value. Alright, so when we did this in the calculator, I'm going to go back to the actual data here. So I'm not going to use the total row right there, I'm just going to use this right here. So we had to use the matrix option on our calculator. When we were using the matrix option, so I'm going to go to, well, first I have to type everything into the matrix. So I'm going to go to second, and the matrix is right there. I'm going to go over to edit. The default in the test is to always use matrix A, so I'm going to use matrix A. And I need a 3 by 2 matrix. When I go back and I look at my data, so then I'm just going to type everything in. So I press type 49 and it's going to go across the rows. Oops, 40. The next one's 15, 27, 32, 30. So now I have everything typed into my matrix. Alright, so where do these expected counts come from? So then what I do is I'll go to stat. I go over to tests, and I go down to the chi-squared test, which should be option C. Alright, by default it's going to want my observed in matrix A. You don't have to put them in there. I always just use it since it's the default. You don't have to type in the expected. It'll do it for you. So I'm going to hit calculate. Now if you remember from class, you kind of have to go backwards a little bit here. So if I wanted to write out, so maybe I would just jot down somewhere. So there's the test statistic, so that 3.22. The p-value is the 0.19989. So again, they're just rounding that up to 0.2. So I would probably, and the degrees of freedom are 2. So I'd probably make note of that somewhere. And then I would go back and I'll go to second matrix again. And now you can either look at it from the name op menu or you can go across and do the look at it from the edit perspective. Sometimes that's a little bit easier. Press enter. And so there's my expected counts. So again, when you're on that step there, the condition check, you still should write down your expected counts. So I would just list those expected counts, say all of them were greater than 5. So the p-value is 0.2. It's greater than the alpha that we chose, so we fail to reject. There's not enough evidence to conclude that the distribution of party affiliation differs, which is not that surprising. We can always do a follow-up analysis if we need to. And all we're going to do with that follow-up analysis is kind of just look at which one's contributing the most. So this is the wine one again. So these are the observed, these are the expected, and then you can see the contribution to the test statistic right here. So the one that's contributing the most is the French music treatment and well, these two, the French or Italian music treatment, and then buying the French wine, I believe that was, or the Italian one. Okay, so those two are contributing the most. That caused us to reject in that first example. In the second example, we did a fail to reject, so there's no point in doing a follow-up analysis. Just watch how you're just watch how you write your hypotheses. Always, the alternative is that at least one of the above or at least two are different. This is another example. I usually opted always to write out just in a word that there's no difference in the 3 treatments, and there is a difference. I'll just go through this here. You can just pause it if you want to read it. Sorry, the calculator or the computer wanted to open something else up. Alright, and here's the test statistic and the p-value and the conclusion. So again, if you want to look at that, pause the video, just take a look at it. Alright, the other types we did here was just a relationship, and I'm going to kind of go through this quickly. So we also still had a two-way table. What's different about this two-way table is there's one big sample here, and then there are categories afterwards. In the other example, there were separate samples. So there was a separate sample for the French wine or for the French music, and a separate sample for the Italian. This one, they had one big sample of 8,474 people, and they just saw how they were allocated. We can look at conditional distributions the same way and kind of just get an idea from the graph. So you can pause this page if you want to read through it. In the test of association or test of independence, we are looking at the generic. The generic for the null is that there's no association between the row variable and the column variable. And the generic for the alternative is that there is an association between the row variable and the column variable. Instead of using the word no association, I could say independent, or I could say no relationship. Instead of using the word association, I could say not independent, or no relation, or there is a relationship. And you can pause this if you want to read through this page. You find your degrees of freedom the same way. Your test statistic is the same way. You can pause this page if you want to look at it in a little bit more detail. So again, you'd still do everything the same. So there's the two hypotheses about this problem with heart disease and blood pressure. Again, here there's only one sample, so you don't have to check the two different ones. The expected counts, I would still list them out, so they already listed them out in that prior page. So if you haven't done that already, list them out there. There's the independent check. There's the test statistic, and again, you can just use the calculator, but always still write out what the first part of the formula is up to the last part. Make your conclusion the same way that we've been doing it. And just remember the difference between the two tests here. So the test of homogeneity, it tests whether the distribution is the variable is the same for several populations or treatments. So remember, there's multiple things here. The test of association independence is for one population, okay? These both have two-way tables, though. You can also, it's like I said, so just look at how that data was collected. So you can pause this if you want to read through it a